Hello, good afternoon, everybody. Good morning. My name is Sherwin Rasuza, the Senior Geoscience Technical Advisor working for CG Geo Software and based in Crowley. Welcome to our webinar today about quantify your reservoir using deterministic inversion. Just some information about this webinar, that you are in the mute mode, and if you have any questions, please type in the chat box that you have, and we will respond those. And we will provide this presentation later on after the webinar. But today the talk is about quantify your reservoir using deterministic inversion. In Geo Software portfolio in CGG, so we are developing and providing solutions for different type of studies for seismic reservoir characterization, which are Hampson, Russell, and JSON. For petrophysics and rock physics analysis, which is power lock, earth model is geological model building, velocity modeling done in the WellPro, and Insight Earth is for 3D advanced seismic interpretation on the post-stack seismic data or stack seismic data or any attributes. Today I will talk about the deterministic inversion methods, which are provided via Hampson Russell and JSON solutions. The outline of the webinar is like this, that I will start an introduction about inversion and deterministic inversion techniques. But what is the seismic inversion? So integration of all logs and seismic data with geological information and transformation of the seismic traces to acoustic impedance or other elastic properties. It doesn't need to be necessarily acoustic impedance. And so through this transformation, we get some description of the earth through rock properties. So if you look at the seismic data, this is one section of the seismic data. It shows you the contrast between the layers and the interfaces of the layers. But if you invert it to the, for example, this case is showing acoustic impedance, it will show you the property of the layer itself rather than the interfaces. So this will help you to identify your reservoir or rock properties much easier than the seismic data. If you look at this cartoon here, so we have Earth. We send this wavelet inside the earth, and it reflects back, and we get the seismic data, process it, and finally we get the seismic. And if we remove this wavelet from the seismic data we have, we can get some elastic properties. And using those elastic properties, we can relate these elastic properties to earth properties. Could be porosity, lithology, fluids, etc. In another view, so suppose this is our earth view, which we have this property, these layers, and it has got hydrocarbon inside in that layer. And if you convert it to the reflectivity, what the reflectivity will look like out of that layer, so we will have some reflection coefficient at the interface of those layers. And then wavelet will be convolved on top of those reflectivities, and finally we will get seismic view. So if the layers thickness changes, what will happen? Let's see, I am changing the thickness, so reducing the thickness of that layer, and you see that seismic view is changing, especially the side lobes of those wavelets are interfering with each other, and they are cancelling each other. Make it a little bit thinner, and at some point the side lobes are increasing the amplitudes of the seismic data. So at that case, we will have very bright anomalies or the amplitude anomalies in the seismic data. And let it go thinner and thinner and thinner. So in some thickness, we are not able to see the layer from the seismic data itself because it's too much thin, and our seismic doesn't have that much resolution. But we need to convert it to somehow to the earth view, which has a higher resolution. So how we can do this? We need to go for inversion, which can be provided by using the rock trace, which is JSON's rock trace or Hampson Russell's strata inversion modules. And how we can estimate the reflectivities, provide the layer or earth view, and we can remove wavelet effects. So, but the question is, does a bit need to be thick to be resolved? So look at this model. We have this red impedance models, and this is the synthetic seismic created using those models. And if you try to invert these modeled seismic data to the acoustic impedance, you see that we can get acoustic impedance nicely matching to the initial model or the starting model. For the thick layer, for the tuning layer, we are still almost trying to resolve it. And you can see that the top and base of the layer is resolved, and also almost the real value of the layer has been, property has been resolved as well. But when it is beyond the tuning thickness, we are not able to get the property value correctly, and we are not able to get the thickness of the layer property. But the area could be it could be resolved. For example, if it is net pay, for example, you're estimating porosity multiplied by thickness, the area which is showing that can be resolved. The seismic inversion in the exploration production workflows is usually around this area, which is seismic reservoir characterization, especially for development planning and also drilling planning. So reservoir characterization is used there. Before that, yes, we use different attributes, 2D seismic, possibly 3D seismic as well, interpretations, but this place we want to go for quantitative analysis and find the bodies and plan the drilling. So in that case, seismic reservoir characterization comes to the effect, and we use it more and more. And also we can give the seismic reservoir characterization models to the reservoir modeling. How we can use a seismic application? So it can improve interpretation using detuning. It removes the wavelet effect. It will give us the layer properties. We can map the reservoirs, extent of it, and geometry of the reservoir. We can find the fluids inside the reservoir, especially if there is a feed gas. We can somehow estimate the density and discriminate between feed gas and commercial gas reservoirs. Reservoir estimates, for example, calculating net pay, hydrocarbon pore volume, etc. Risk assessment and mitigating the risks using the probability volumes we can calculate. Mapping fracture reservoirs, well placement and well path design, reservoir monitoring in field wells, and enhanced recovery strategies. Identifying overpressured zones, mitigating drilling hazards. So if you see any overpressured zones due to the velocity changes, we can identify those in the inversions as well. And finally, we can get inputs to the dynamic reservoir modeling. And many more applications of the inversion. But what is the deterministic inversion? Deterministic inversion will produce what we consider the best single solution to the seismic data. It's like your example is a best least square solution to a problem. For example, we are doing regression and you're getting one regression which is fitting to your data. It is one best solution. It is not necessarily the correct solution, but it is one of the one best solution. And its resolution is about same as the seismic resolution, a little bit higher, and it also includes the low frequency that seismic doesn't have. I will explain a lot about that. But considering the seismic data we have, so we can have different deterministic inversion methods. For example, if you have a single stack data, it includes post stack or one angle stack, for example. For post stack, we can go for recursive inversion, colored inversion, elastic impedance inversion, model-based, and constrained sparse spike. Model-based is main tool in Hampson-Russell, and constrained sparse spike inversion is main tool in JSON. Pre-stack seismic data if we have, so in that case, the inversion or some sort of inversion could be extended elastic impedance, and we can go for simultaneous AVO inversion or AVA inversion. This could be model-based or CSSI again, based on what solution you are choosing. And for pre-stack azimuthal seismic data, we go for anisotropic inversion, which is available in JSON, and anisotropic in study in Hampson-Russell. For these seismic data, if you have, you can go for time-lapse inversion, and for multi-components data, which is PPPS seismic data, you can go for multi-components PPPS inversion. So based on the seismic data we have, which elastic properties we will get? For example, if you are talking about zero offset seismic data, we are assuming that the seismic goes down to the reflective reflection point and goes back with the zero offset or zero angle to the interface, or normal to the interface. So in that case, reflectivity could be from differences of the acoustic impedance between the layers. This multiplication rho V is acoustic impedance. And if we invert these stacked seismic data, we can get estimation of the acoustic impedance of the layers. But if the incident wave is not normal to the interface, then there is an angle between the normal to the interface and the ray, which is the wave which is hitting the interface. In that case, we will have a reflected P and S wave and transmitted P and S wave. In this case, our reflectivity, which usually we are dealing with the PP seismic data, is a function of the velocities of the two layers, densities of the two layers, and also the angle of the incidence. So by inverting this type of data, we are able to get VP, VS, and density, or combination of these parameters like shear impedance, acoustic impedance, VP, VS, or you can convert it to other things like lambda rho, mu rho, etc. But if there is anisotropy and our wave is hitting to this anisotropic planes with an angle of which has its azimuth, in that case our reflectivity, which is PP, again we are talking about P wave recording, then it will be a function of the incident angle and plus the azimuth of that anisotropy, and plus anisotropic parameters. So for this case, I'm showing the Thomson parameters, which is used for anisotropic estimation. So using these pre-stack azimuthal seismic data and inverting those, we are able to get the elastic parameters like VP, VS, and density, magnitude of anisotropy, and direction of the anisotropy, or say fractures. So just a cartoon showing we have post-stack seismic data. So the incident angle is normal to the interface, and we have angle stacks or different angle gathers, and we have the different theta other than the 0 theta. And we could have same settings for this pre-stack data, but at different azimuths. So we can also sort our data sets based on different azimuths and with different offsets. So these thetas are the incident angle, these azimuths are the different azimuths. And if you use different seismic data, we can get a different geological value out of those. For example, this graph is showing for full stack seismic data, we can go for geometric attribute analysis or full stack inversion. We get some geological value out of that, but you are increasing the geological value using sophisticated data and more data sets. And finally, you go for azimuthal data sets, and you can get anisotropy estimations and using anisotropic inversion. But deterministic inversion methods. But before going to deterministic inversion methods, I just want to show that how the low frequency is important. For example, we have this Earth and its reflectivity. So we send wave, and it will create us this post-stack seismic data, and we can calculate seismic from that. And seismic coming out of the Earth, and we record it and process it, we can do remove the wavelet after that, and we can get the reflectivity. But it lacks one important information, which is low frequency part or the trend of this data, and we need to add it from some known information from, for example, from well-log data. Then adding that, we are able to get impedance correctly, absolute values of impedance, and from impedance we can infer the geology behind that impedance. I talked about the low frequency. Let's look at this in the frequency domain. So I have a layered Earth in here with its own acoustic impedance, and I can calculate reflectivity using those formulas, and I can calculate seismic out of those using the convolution. But in the frequency model, if you look at those in the frequency model, so the amplitude spectrum of the Earth, it shows starting from 0 Hertz to some maximum Hertz and with some slope on it. And if you look at the amplitude spectrum of the wavelets, it has got some missing data sets here at the 0 Hertz, 0 to some low frequency Hertz. And they are applied on each other in the frequency domain like a multiplication. And the effect will be like this. So the seismic data will have this seismic bandwidth or the frequency spectrum. And we are lacking this low frequency part, which is very important. It is like a trend you need to apply on the inversion to get absolute values. So we need to create a low frequency model on every deterministic inversion which we are doing based on the seismic data. It could be very high. Let me go back again. So for example, for broadband seismic data, our cut is very close to the zero. It's not zero, but very close to the zero. So we have more data content or more low frequency in the broadband seismic data. So go back to the deterministic inversion methods, starting with the recursive band or band-limited inversion. So in the zero offset seismic data, we know that this reflectivity is coming from this formula. So if we somehow calculate the reflectivity for out of seismic data using removing this wavelet, we can calculate the acoustic impedance for each layer using this some algebraic calculations, and we can calculate acoustic impedance for each layer using the acoustic impedance of the previous layer, or in a general term using this formula. So it shows that we can calculate acoustic impedance using the acoustic impedance of the initial layer or the layer before. This easy way to calculate acoustic impedance, and in this case the simple form of the inversion is this, and we are assuming the seismic data is reflectivity. We are not removing the wavelet. You can also remove the wavelet, but for general form, which was when this introduced to the industry, it was just using seismic as it is and assuming that the seismic has zero phase. But yeah, the issues with this wavelet is ignored, and each seismic sample is treated as a reflection coefficient. Assume seismic is zero phase, which is not the case every time. And even if the seismic is zero phase, side lobes of the actual wavelet will be interpreted by the algorithm as lithologic variation, which is not the case because just the wavelet, side lobes of the wavelet. And the inversion result is band limited to the frequency range of the seismic data. It is a good tool for quick qualitative interpretation. In a big area, you want to do quick stuff to find anomalies. And this is the one result. So in the left, you have seismic, and at the right, you have band-limited inversion results. Colored inversion, it is one step forward out of that colored inversion. So we are saying that rather than doing a recursive inversion, say find the operator that if when I apply on the seismic data, I got my acoustic impedance. And this operator is calculated in the frequency domains. How we do this? For example, you have this acoustic impedance from the logs. You can calculate the frequency spectrum of that log, and you can convert it to a logarithmic scale and fit a line to that. And then this line can be shown here in this amplitude spectrum of the seismic data, which is in blue. And this will be our target, red one. And we want to transfer our blue spectrum to red spectrum. And we know that the phase of that signal should be 90 degrees. Then just easy dividing this blue to red, we can get this amplitude spectrum of the operator. And we know that it's a 90-degree frequency, then we can calculate it in time. So then we can apply this operator on seismic data and we can get the acoustic impedance. It's very easy tool as well. It's not depending on an initial model, but needs well to determine the impedance frequency trend. Very fast to apply, assumes the data is zero phase again, and produces a result similar to recursive inversion, but with higher frequency content and better scaling. Again, this is a good for quick qualitative interpretation. And you can see here that colored inversion is provided here, absolute value and relative value. You can have this low frequency part added to the inversion results, and you can get the absolute values. Model-based inversion is another way of doing inversion, which is main focus of Hampson-Russell stratum. It uses this formula, which is a seismic equals wavelet convolved with the reflectivity plus some noise. Assumes that the seismic trace and the wavelet are known, which is the case. We know the seismic, we estimate the wavelet, and assumes that the noise is random and uncorrelated with the signal, and solves the reflectivity, which satisfies this equation. So iteratively change R until you satisfy that based on these known values, you can this equation is holding. and solution is done iteratively. So how it is done? So we have this initial model here in the left-hand side, and reflectivity can be calculated from that model. Convolve with the wavelet, we can get the synthetic seismic data and compare it with the real seismic. There will be some differences. You need to apply the differences on the model, update the model, and finally you get the final model and less differences. It's shown here, for example, the red one is my initial model and the blue one is my log. And this is synthetic seismic data. First iteration, nothing there because there is not much changes in the red one. And my seismic data, I have lots of differences between synthetic and seismic coming from immersion. So I iteratively changed the model, so you see that model has been changed and changed and changed and changed, and finally you get less error and better matched of your log to the inversion results or the model. So this final model will be your final results, and you can use it for quantitative interpretations. Example shown here at the left-hand side, we have acoustic impedance inversion coming from model-based inversion. At the right-hand side, we have residuals of those inversion. In Sparse spike, which is main tool in JSON, we are assuming that the Earth has, if you look at this reflectivity of the Earth, there are some noise background of the reflectivity and also the main events which are relating to the geological events are these big events. So in the sparse spike, we are looking for this sparser spike, which means this in the middle one, which has a sparser spike, but these spikes they have geological meaning, they are not noise. So the sparse spike uses this idea to calculate the model of the Earth. And it is also done iteratively. This example is shown here. So we start with adding spikes to the models of our seismic data in here, and this is the dots are showing how much the seismic is not modeled. So here, first one, okay, we are modeling the modeled energy 42%, and next spike is added to the to satisfy the next event here, and you are seeing that it's getting. This part is getting modeled. Next spike is added. Then next spike is added. Is it correct or not? No, it's because we have still some energy left there. We need to make it 100% energy matching to the seismic data. So then this iterative method will give us the final result, which is this sparse spike model of the reflectivity of the Earth. Then we can convert it to the acoustic impedance, and we can add the low frequency part which is missing. Then we can get the absolute values of the impedance. And finally we can compare it to the seismic data. In constant sparse spike inversion in JSON, we have stack seismic data, post-stack, for example, or pre-stack as well, the same. We create, estimate the wavelets from the logs at from the seismic at the well locations. We create a low frequency model using the logs and horizons, or combination of logs, horizons, and the seismic velocity. And we do the inversion, and we get the final P impedance model. Constraints are helping us to limit the solutions to the geologically meaningful solutions, rather than every value can be used as to be used in a formula that calculates the reflection coefficients, but they are not geologically meaningful. So we use constraints to constrain those results in a geologically meaningful limit, and also we can also add our geological knowledge to that constraints. For example, it's shown here. Our objective function will be function of the contrast, which is how much the solution can be sparse. The match to the seismic data, which is the synthetic from immersion minus seismic, and some trends here which is applied to honor the geology or the lateral variation of the geology. So this objective function is optimized, and we get the optimum optimum reflectivity and optimum seismic noise. Example shown here. So for example, it's the deterministic inversion is helping the interpretation. This is one section coming from the I think Southeast Asia. So we have interpretation from the left-hand side and also right-hand side. We need to interpret in between. we don't know how to interpret, and if we do the inversion, we see that interpretation should include this channel here. So if we haven't used this inversion, we could have lost this channel here. So if we, for example, one interpretation could be like this, and we could easily miss that channel here. Another example is here how interpretation inversion can help us to find the better prospect information. So this one is showing the seismic, and we have two layers, upper layer and bottom layer. Bottom layer shows seismically higher amplitudes, but if I invert it to acoustic impedance, the upper layer is showing better amplitude and connectivity than the bottom layer or lower layer. So why this is happening? So we have this seismic amplitude extractions at the left-hand side at the upper sand and lower sand layers. And as you see, this upper sand doesn't show continuous body, just broken bodies. Maybe commercially, I don't like to drill these bodies, and I opt for these bodies, and continuously they are continuous and very bright amplitude. But doing inversion, we get better continuity in the upper sand and very bad continuity and just very small bodies, I can say, in the lower sand. Why this is happening? Because we have this tuning effect is happening here. So in the top sand is at the tuning and at the seismic section, you see that it's not showing me the sorry, the bottom sand is showing at the tuning effect, at the maximum tuning, it will show the brightest spots, and the bottom, the top one is at this location, so it's not showing that continuity or the good amplitude in the seismic data. But after inversion, you get better amplitude and better connectivity for the upper one. Seismic inversion can also be used to thickness map estimations. For example, this is showing thickness map has been captured, thickness of the body has been captured in this top of this reservoir, and these are the wells has been drilled after inversion at the correct location. So this inversion has helped planning the drilling locations in a good way. So elastic impedance is another stacked seismic data inversion. This stacked seismic data could be angle stack. So for each angle stack, you can calculate elastic impedance for that specific angle or theta. And this elastic impedance is some sort of calculations coming from, for example, from these equations. If you consider the two-term accurate charge equations, similar to acoustic impedance inversion, you have fully stacked seismic data or zero offset seismic data. You can remove the seismic wavelet from that, and you can get reflectivity. From reflectivity, you can get acoustic impedance. And the same workflow can be applied, and at that angle stack, you remove the wavelet for that angle stack, and you get the reflectivity for that angle, and from that reflectivity you can get estimation of the elastic impedance. This elastic impedance can be done separately for each angle. So for example, angle stack, for example, for this one, they have for 7.5 degree angle elastic impedance and for 22.5 degree elastic impedance. Near and far. There are some changes in the, you can see in this reservoir point. So the nearest stack doesn't show, but farthest stack shows some variations. We can use this type of changes to do some interpretation of the elastic impedance. For example, we can do the cross plot of near elastic impedance and far angle elastic impedance, and we can identify the points which are sweet spots for us, and we can capture those bodies in the elastic impedance volume. And this is also another way of calculating or interpreting the reservoir. It's also qualitative. Going forward to pre-stack seismic data. So we have one extended mode of the elastic impedance, which is called extended elastic impedance, because this elastic impedance has a scale problem. For example, if you go back to that equations, For the higher angles, this elastic impedance value will be different than the near angles because this sine square are the theta is sine is squared, and the values will be very different. So to correct for that, Wittekam introduced this extended elastic impedance equation using this chi angle. And for that chi angle, so you can correlate extended elastic impedance coming from this formula with some of the rock properties which is target for you. For example, for this case, I am showing the extended elastic impedance calculated from logs for different chi angles, and I have a VPVS ratio log, and we have lambda log, K log, and rho VS, and also mu log here. And at each theta, so at each chi, so for example, if I want to estimate VPVS out of seismic data, I can just apply extended elastic impedance of 45 degree, and I can estimate VPVS. Then I need to scale it to proper VPVS value. Extended elastic impedance is good tool. It uses quick AVO modeling and AVO stuff. It can be used for qualitative measurements and interpretations, but go forward for quantitative inversions. We go for simultaneous inversion. In JSON, we use rock trace, and in rock trace, we import all the angle stacks, could be gathers or angle stacks. For each angle stack, we calculate a wavelet for that specific angle stack. And within the process, these three steps are done. So we estimate contrast for the parameters from the inversion. One contrast means this reflectivity, for example. And these reflectivity or contrast are converted to elastic properties later on. And elastic parameter then estimated afterward in the inversion. So we will use low frequencies and also constraints. Low frequency to add to the missing part which is not available in the seismic data, and also as a constraint as well. And then you can get P impedance, S impedance, and density, or VPVS. Using those equations, you can relate them to, using those parameters, you can relate them to phases, porosity, or folates. The objective function in JSON, it uses sparse spike inversion, and it's a function of a contrast again for different properties. Seismic signal to noise ratio, and also the seismic to synthetic match. And then we have this geological constraint that you can have, for example, trends, spatial constraint, Gardner and Modrak to relate, for example, VS to VP or density to VP, and some functions for the mathematical calculation of the matrices. In Hampson-Russell, we know that there is a relationship between the ZP, ZS, and which is acoustic impedance and shear impedance in the wet rocks, and also which is that was coming from the Modrak line. And also we have this Gardner relationship, which is relating density to the VP. So these formulations has been applied in Hampson-Russell using the Fatty's equations and also some combination of the AVO calculations. Finally, these equations will be used in Hampson-Russell, so we will apply this trend for the wet logs, and this trend is for the wet trend. And the delta LD, which is here, showing that for example, hydrocarbon is coming in that region, so we are trying to find those the parameters ZP, ZS, and density from iterations to find the best matching of the seismic to the synthetic. So it's done here. We start with initial model. We calculate reflectivity for each theta using this initial model, which is in the black log here. It uses Fatty's equations in the AVO, and we calculate reflectivities for each angle and synthetic gather compared with the real gather and the differences. And the differences are used to update this initial model. Finally, once the initial model updated and we get the less differences for the gather, the ZP, ZS, and density will be the final results or final model, which are also matching to our logs as well. So in simultaneous inversion workflow, we have either angle stacks or gathers. We have well logs. We have interpretation of the horizons. So we use we can use petrophysics rock physics model to condition logs. We can do then well to seismic time and estimate wavelets. And once we have wavelets, we can go for inversion. Inversion could be simultaneous inversion in Hampson, Russell, or JSON. We need to have these low frequency models for JSON and as an initial model for Hampson, Russell. And then we do the inversion, we find our properties. The next step will be interpreting properties that could be done using the cross-plotting technique and also body capturing or other techniques, or we can also calculate other properties like lambda rho or mu rho. Example shown here for carbonate case, we have a seismic section here, we have tight carbonate here at this level. We have gas carbonate, which is dolomite here, and we have tight again here. If you look at the seismic data at this location, you don't see that much changes, but there is some strong amplitudes in this gas anomaly section and nothing here. Then after inversion, simultaneous inversion and converting to lambda rho and mu rho, we can do cross plot of lambda rho and mu rho. We can also identify the zones of the, for example, this is porous gas reservoir, and we can identify those on the, for example, lambda rho or mu rho. And this is identified here, so you see that this has captured in the reservoir. Another example is here, so we have angle stack seismic data here, so we have 3 angle stacks. This is for unconventional seismic, unconventional reservoir, so the idea was to estimate the suited places for drilling and fracking. So we can estimate P impedance, VPVS, and density by simultaneous inversion. The logs are shown. You can see that they are very good matching to the inversion results. We can convert them to these elastic properties to Poisson ratio, for example, or Young's modulus and brittleness index. There are some formulations for these properties calculated from P impedance, shear impedance, and density. And then closure stress scalar can be calculated, corrosion content can be calculated, and effective porosity can be calculated using those parameters. And finally, V-quartz and also brittleness index. Using these two, we are able to identify brittle and promising locations. And the cross plot is shown here, which is showing 5 different facies, and PDFs fit to those facies to be able to apply it on the inversion results. And finally, the inversion results end up with these facies, which the green facies is the best facies to drill and frack, which is shown in 3D here as well. Another example is for broadband seismic data here. So we have 3 angle stacks broadband seismic data converted to acoustic impedance and VPVS using the simultaneous inversion. Then we have used again which is called LithoSI here. We can use different tools here, LithoSI and FFP. We have different webinars for those, and we can refer to those webinars. But the idea is to calculate probability of each facies using the inversion results, for example, IP and VPVS, similar to the previous example. So in this case, we have estimated the probability of the gas sand using these 2 elastic properties, and they are matching to the gas sand facies and the well log, which is shown on top of this section. So we go for pre-stack azimuthal seismic inversion, and we have anisotropic inversion, which is patented by the CGG solutions for HDI media. Inputs are azimuthally sectored offset or angle stacks and common azimuth gathers. Minimum we need 6 common azimuth gathers, 6 azimuths. And deliverables are anisotropic orientation and magnitude of the anisotropy. Weakness, fracture density could be interpreted out of those information, and VTI, HTI is also possible to handle these cases of the VTI, HTI anisotropy. The values, laterally varying wavelet compensated reservoir properties can be applied, and inversion properties calibrated to the well control. How it works? Uses a simultaneous inversion of the inversion, which is rock trace, and then we estimate acoustic impedance or elastic properties like acoustic impedance, shear impedance, and VPVS for each azimuth. And we use another tool which is called elastic volume evaluator, which converts these elastic parameters at different azimuths to anisotropy and its direction. Example shown here, the workflow, we have gathers, so at different offsets or angles at different azimuths. Then we do use rock trace to calculate VPVS density and, for example, acoustic impedance for each azimuth. And then we use elastic volume evaluator, for example, to fit HDI model, and we estimate anisotropic parameters. Could be these values, which is coming from the Fourier coefficients, R0, R2, and R4, and also the direction of the azimuth. Example shown here, we have azimuth. One of the azimuths is shown here for different offsets. So we have 6 offsets for one azimuth. So we had 6 other azimuths as well. And so using this rock trace, we can convert those different azimuths gathers to VPVS at those azimuths. This is the results of that. So we have azimuth 1 VPVS up to azimuth 6 VPVS. So you see some differences between the azimuths at that reservoir level. So for example, this part is a little bit less if you compare to these 2 azimuths or this one azimuths. Using this EVE, elastic volume evaluator, it was possible to calculate the azimuth of that anisotropy and also the magnitude of the azimuth, which is B1 shown here. And if you see them in the map view, this is maximum VPVS has been recorded or inverted and found out that this is the maximum VPVS, and the VPVS anisotropic amplitude, and also azimuth of the major axis is shown here. So you see that there are some channels that has been identified and some lineament in the reservoir zone, which is almost east-west here and north-south here at this location. So different regimes of the stress or fracturing could be inferred from these azimuth of the major axis. Another example shown here. So at the left-hand side, magnitude of the anisotropic has been calculated. And these are the faults, the black ones. And you see that at some fault locations, we have higher anisotropy. And this faulted location has higher anisotropy, especially this location. These purple ones are the well locations. And this map, the right one, is showing the azimuth of the symmetry axis of the anisotropy, which is perpendicular to the for example, direction of the fractures, which is following this. For example, for this brown one, which is north-south, it should be this direction, and then we will have almost this direction, the faulting direction, so which is almost matching to the faults here. Or for example, for this case, we have this north-south here, but as the symmetry axis azimuth, but the fault axis is parallel to what has been estimated as the azimuth of the anisotropy, which is 90 degrees to the azimuth of the symmetry axis anyway. Another example is shown here. So at different wells, we have azimuth of the VFAST from the cross-dipole acoustic log, which is measured in the well. And these arrows are the azimuthal inversion and the direction coming from the azimuthal inversion. So you see that they are confirming each other at different wells, well A, well B, well C, and etc. of these 8 wells. Right, so there are many options starting from a post-stack, fully stack, angle stack, and azimuthal data sets. We go for 4D seismic data on time-lapse inversion. As you know, for time-lapse, we start with 3D base, then we go to start producing, and then we acquire another seismic data, maybe a few years later, 1 or 3 or many monitor seismic data acquired. Then we find the differences between the seismic acquired and the base seismic. Then we find the differences, and these differences will tell us the fluid changes or structure changes. So for the inversion, in this case, it could be based on the invert bases and monitor surveys individually and interpret the differences of the results, or invert all seismic surveys simultaneously and estimate the differences. One option is shown here, or one example is shown here, inverting monitor surveys and the base surveys differently or separately, and find the parameter that which shows the fluid changes, which for in this case the difference in the acoustic impedance was the indicator for the fluid changes. So this is showing a difference in the acoustic impedance, and this one is showing the criteria, which in this case was showing where is the reservoir and where is the non-reservoir. And this is coming from the base, so it doesn't change where is the reservoir versus non-reservoir. The only thing is changing is the fluid is changing. Then we can find some areas that, for example, for this case, if I go to the next slide, this part is a gas coming out of solution, this area, and this place is water replaces oil. So if you go capture those bodies in the 3D viewers, you can see that these are the locations of the gas out of solutions, which also wells confirm this. And the right-hand side, which is water replaces oil, and the water comes to the reservoirs, and this is also confirmed because the water injection was ongoing in the field. Another case study is the generation of the fluid changes probability cubes. So we are talking about, again, inverting separately and interpreting the results. So we have IP or acoustic impedance of the monitor over acoustic impedance of the base, and VPVS base to VPVS monitor. So if it is a flood, gas flooding, and you can calculate the probability of having a gas flooding, which is saying changes of the gas saturation more than 50%, you can identify those, and it has been identified. Or for uppercase, water flooding was also ongoing for this specific case, and they were able to find the probability of the areas which the variation of the water saturation was more than 50%. So another example is shown here. A simultaneous inversion of the base and monitor was done. So the idea was to find out the path flow for the water. So we have this injector well here and the producer well 2. Well 2 is a injector and the producer is well 3. And you can see that from this pseudo-weakly calculated from inversion and this delta IP from inversion of the simultaneous inversion, it shows that the pathway from the well 2 to well 3 is how it is happening. So maybe they can avoid the water cuts by controlling the water injections. This example shows the inverting the different seismic, and the idea was to find, this is a heavy oil, and the idea was to inject steam and produce the oil, and the steam chamber was in the layer which was thick enough, also it was affecting the seismic data, and you can see the band-limited inversion has been calculated here using the simultaneous band-limited acoustic impedance, and band-limited VPVS has been calculated using the simultaneous inversion, and we are able to find this location of the top and base of that layer. Then this low frequency model needs to be updated for that inversion to be able to account for the changes so in the chamber. So this is in the right hand side, you see the low frequency model variations or changes has been applied. Then after applying that the low frequency variations, you can get the full bandwidth P impedance, which shows that how the acoustic impedance has been changed due to this steam injection. So you can monitor the steam injection or steam front. So in deterministic inversion, we have different methods. As I mentioned, I didn't go for multi-component. We will have different webinars for that. If there is any question, please let me know by typing it there in the panel you have.
All right, so I do have some questions. For the sake of time, I'll just go through one of them. So for one question is, in 4D inversion, do you use the same low-frequency model for both base and monitor, or do the starting models vary to reflect reservoir changes?
Okay, so that's different scenarios. So for this specific case, as I showed, we use different low-frequency models. So we update different low-frequency model. You can also use a different velocity model or different low-frequency model to account for the velocity variations as well. Yes, you can apply different techniques at different situations.
Okay, great. And like I said, for the sake of time, we'll follow up with the other questions. So let's move on to how you can get more information and contact our presenter.
Okay, so the last one. So this is my contact. So if you want to contact me, please use this email. And you can also contact us using this through software support and regional contacts.
Yep, and if you have any other general information or would like more information on other applications, you can also send an email to gs.solutions. And with that said, we thank you for joining today's webinar.
Thank you very much, everybody. Bye.